this video, we're going to look once again at the central difference method. So we were looking at this method in the previous video, but we were using it to calculate velocity based on some time and position data. In this video, we're going to calculate acceleration, but it's a very similar method. In fact, it's basically exactly the same. So I would highly recommend you watch the previous video first and then watch this one. So the example is to calculate the acceleration for frames 3 and 4 using the central difference method, and that's using the information in this table. So we can assume that some experiment has been done, say where a particle is moving, and every so often at certain points called frames we record the time since the experiment started, so since the particle started moving, and we record its velocity at that point. And if we have time and velocity, we can calculate acceleration at these discrete points. And we do that using the key fact that acceleration is just the change in velocity over the change in time. So that's just a general definition. When we talk about acceleration, we mean how much did the particle's velocity change over a given time period. That is its acceleration. But when using the central difference method, just like we said in the previous video, we're only concerned with the information from the frame directly after and directly before the frame we're looking at. So it's a bit counterintuitive, but say for frame 3, we don't worry about the information recorded at frame 3, we worry about the information from frames 4 and frame 2. We calculate the difference, so the change from 2 to 4 and in time and in velocity, and we can use this to find out what the acceleration must have been at the midpoint being frame 3, because if you look, our times are actually regular. If you calculate the difference between any two times from one frame to the next, it's the same. So that's the idea. It's just like in the previous video, so let's just have a look. Let's have a go at it. So frame 3. First, we want to use the information from frames 2 and 4. So the times and the velocities, and we want to look at the change, so the difference from frame 2 to 4. So we subtract whatever the information was in 2 from the corresponding number in 4. So we plug into that equation, we do that, we get 2.4 minus 6.59. So this is the change in velocity, so we always subtract the one from the previous frame from the one from the next frame because we want the change. So here we're going to get a negative number when we do that, but that's okay because acceleration can be negative. And so that's divided by 0.0501 minus 0.0167, so that's the change in time. We get minus 4.19 over 0.0334, which is roughly equal to minus 125.45 meters per second. So let's put that in our table, minus 125.45. So that was the acceleration at frame 3. And we do the exact same thing for 4. So we're going to we look at frame 4, we need the information from frames 3 and 5. So the times and velocities. Plug into the equation. We get minus 2.10, so remember the sign, minus 3.59. So that's the change. That's going to give us the difference between the two. Again, always subtract the one from the previous frame from the one from the next frame. And then we get that divided by 0.0668 minus 0.0334. We get minus 5.69 over 0.0334. So the change in time is the same because we were taking the recordings at regular time intervals. That's why we would expect the change in time to be the same, and it is. It's only the change in velocity that is different because the acceleration isn't constant. So the particle is clearly speeding up, slowing down at different rates at different times. So put this into a calculator and we get roughly minus 170.36. So we'll put that into our table as well. And that is the answer. So if you combine this video with the previous video, if you watch them both one after the other, you can see that in the previous video, using time and position recordings, we could calculate velocity. Hence, if you do that and write the velocities down on the table, you could then use the time and velocity recordings to calculate acceleration. So as long as you've got time and position, you can actually calculate velocity and acceleration using the methods in this video and the previous video. So in both cases, you'll be using a version of the central difference method. So it's an important method to be aware of.